Isaac Newton contributed the new three laws of motion that have paved the way for a further understanding of forces and um, how forces deal with real life interactions. So in this video, we will talk about the Newton's first law, but we will start with this statement. So if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. This may be different from how you recall first law is defined, but this is more like how Newton stated it. But in order to understand this, let's first talk about a reference frame. So a reference frame is simply a way to observe moving objects. So when you see a moving object, of course, you, the person who is seeing the object, is in a reference frame. There are many ways that you could see the moving object. Maybe you are standing still while looking at the object. That means that your reference frame is stationary. It is also possible that you are moving while you are looking at a moving object. Maybe you are moving at constant velocity. Maybe you are riding a car while looking at the object outside of your car. So in that case, your reference frame is moving with constant velocity. Maybe you are riding a car that is accelerating. So your reference frame, while observing other moving objects, is an accelerating reference frame. According to Newton, in his first law, if you see an object that has no interaction with other objects, so that means that it has no force with it has no force with other objects. It's not being pushed, it's not being kicked, or whatever. Or maybe it is push and kick, but overall, the net total force acting on it is zero. Then it is possible now to identify a reference frame in which the object has zero acceleration. A reference frame in which the object has zero acceleration is called an inertial reference frame. There are two kinds of inertial reference frame. One in which the observer is standing still, and another in which the observer is moving at constant velocity. Sorry. So, for example, no, when you are on a train moving at constant velocity, any reference frame that moves with constant velocity relative to an inertial frame is itself an inertial frame. So when you are in an inertial frame of reference, like when you are standing still and looking at an object, if that object that you are looking at has zero net force, let's say, for example, you are looking at a chair that is standing, that is still in the ground. Actually, there are two forces acting on the object. It has two interactions. It is interacting with the earth, and then it is also interacting with the ground. The sum total is that the total force acting on the chair is zero. So you can say that essentially the object has a net force of zero. And so it is possible, according to Newton, that you can that object will have zero acceleration as observed from a certain inertial frame of reference. And indeed, when you look at the object and you are at an inertial frame of reference, you are just sitting still or standing still while looking at the object, you see that indeed the chair has zero acceleration. So that's how Newton defined the first law of motion. But we're probably more familiar with the other ways that the other way that Newton defined it. The reference frame that moves with constant velocity relative to distant stars is our best approximation of an inertial frame. For example, when you are sitting still, then with respect to the stars that seem to be the distant stars that seem to be stationary, then you are in an inertial frame. Or when you are moving, walking at constant speed, with respect to the stars, then you are in an inertial frame. But sometimes, no, we also consider the Earth as an inertial frame. So when you sit still with respect to the Earth, then you are in an inertial frame. You can observe the world and can say that you are in an inertial reference frame. Or when you are moving in a car and the car is moving at constant velocity and you look outside, you look at objects, and the car is moving at constant velocity, you can say that you are in an inertial reference frame. The Earth is not really an inertial frame because of its orbital motion around the Sun and its rotational motion about its own axis. But we just approximate that it is. That is a very, not really a big approximation, but a considerable approximation. Now, this is the definition of Newton's first law that you're probably more familiar with. So in the absence of external forces, and when viewed from an inertial reference frame, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. That is, with a constant speed in a straight line. This is known as the practical statement of Newton's first law. So when you're looking at an object from an inertial frame, either you are sitting down or you are moving at constant velocity, and you see that there are no external forces acting on an object, which is impossible in this Earth because there are so many forces, so many interactions in this Earth, gravity being the biggest one. Maybe if you look through a microscope or a telescope, or when you are able to go to the far reaches of space, far from all the planets, far from all stars, with zero gravity, and you happen to see an object there. When you look at the object, there are no forces acting on it. When there are no forces acting on an object, the acceleration of that object is zero. That object is not accelerating at all. So it turns out that when objects are accelerating, you are definitely sure that there are forces acting on that object. Any isolated object, one that does not interact with its environment, either at rest, it stays at rest. Or if it is moving at constant velocity, it stays moving at constant velocity. In fact, the word inertia has been invented, and inertia is a tendency of objects to resist any attempt to change its velocity. Therefore, accelerating objects must be experiencing a force. And with that, we can define a force as that which causes a change in the motion of an object or the velocity of an object. Let's look at this quick quiz. Which of the following statements is correct? A, it is possible for an object to have motion in the absence of forces on the object. B, it is possible to have forces on an object in the absence of motion of the object. C, neither statements A nor statement B is correct. D, both statements A and B are correct. What do you think? Letter D, both statements A and B are correct. Choice A is true. Newton's law, first law, tells us that motion requires no force. An object in motion continues to move at constant velocity in the absence of an external force. When you see an object that is moving at constant velocity, it is possible that the net force on that object is zero. It is just in a state of constant velocity. And the only way for that to change is if a force acts on it, either to slow it down or to speed it up. So there's nothing special about the object moving at constant velocity. And in fact, that's how comets and asteroids continue to move forever, because along its path, there are times when the net force acting on them is zero. When they are far away from the sun that they are orbiting around, those are times when the net force on them is zero. That doesn't make them stop. That just means that they will go on with their current state of motion, which is constant velocity. They will carry on moving at constant velocity. And when they get to be closer to the sun again, the sun will have a more significant interaction with them, causing their motion to change, causing them to turn around, revolve around it, or around the sun, and change direction and swing out again. The absence of force does not cause an object to stop. It just causes the object to go on, to carry on with its current state of motion, either at rest or moving at constant velocity. Choice B is also true. Stationary object can have several forces acting on it. But if the vector sum of all of these external forces is zero, there is no net force, and the object remains stationary. When you are sitting down stationary on a chair, you are interacting with the chair because your butt is touching the chair, and you are interacting with the earth because we are all in the presence of the gravitational field of the earth. But overall, when you vector sum these forces, the total is zero. So you carry on with your current state of motion, which is being at rest. So that is all, and thank you.